In this module, we will be learning about international units of measurements. Any physical quantity such as length, mass, or time is measured and denoted in terms of their standards called a unit of measurement. A unit is an internationally accepted basic reference standard against which the measurement of any physical quantity are compared. In physics, we deal with many physical quantities and their units. However, very few basic units are required to express these physical quantities. Most physical quantities are expressed in terms of some base quantities. These base quantities are referred to as fundamental quantities. For example, distance, which is a measure of length, is a fundamental quantity. It's the same with time. The other quantities, which are expressed in terms of their fundamental quantities, are called derived quantities. For example, area or volume, which is expressed in terms of multiples of length, is a derived quantity. Similarly, speed is a derived quantity, as its measurement depends on distance and time. The units of fundamentals or base quantities are called base units or fundamental units. The units of derived quantities are expressed as a combination of base units. Such units are called derived units. Base units and derived units together make up a system of units. A system of units is generally accepted set of units of measurements. Until recently, three major systems of units were in use in different countries based on the units of three fundamental quantities, namely length, mass, and time. Among these were the CGS system, which stands for centimeter, gram, seconds, and FPS, which stands for foot, pounds, seconds, respectively. These units were adapted by Britain and hence the system is referred to as a British system. The third system of units is the MKS system, which stands for meter, kilogram, and second. However, in 1971, the General Conference on Weights and Measures recommended a standard set of units of measurements with their symbols and abbreviations. This system is known as Système International des Units, French for International System of Units, abbreviated as SI. Currently, SI units are followed globally for all scientific, academic, commercial, technical, and industrial purposes. In SI, there are 7 base units for the 7 physical quantities taken as fundamental quantities. Following are the quantities and their corresponding units. Length is measured in meters, denoted by the small letter m. Meter is the length of the path travelled by light in a vacuum during a time interval of approximately 300 millionth of a second. Mass is measured in kilograms, denoted by small letters kg. Kilogram is equal to the mass of international prototype of the kilogram, a platinum radium alloy cylinder kept at International Bureau of Weights and Measures in France. Time is measured in seconds, denoted by the small letter s. A second is the duration of approximately 9 billion periods of the radiation, corresponding to the transition between the 2 hyperfine levels of the ground state of the cesium-133 atom. Electric current is measured in ampere, denoted by the capital letter A. An ampere is that constant current which, if maintained in 2 straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 multiplied by 10 raised to the power minus 7 Newton per meter length of the conductor. Thermodynamic temperature is measured in Kelvin, denoted by the capital letter K. A Kelvin is a fraction, 1 over 273.16 of the thermodynamic temperature of the triple point of water. Luminous intensity is measured in candela, denoted by the small letters CD. A candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 power 12 Hz, and that has a radiant intensity in that direction of 1 by 683 watt per steradian. An amount of substance which contains as many basic entities such as atoms or molecules in a system as equivalent to the number of atoms in carbon in a 12 isotope is measured in mole, denoted by the small letters MOL. Apart from these basic units, SI has defined two more units for two supplementary quantities, namely plane angle and solid angle. Plane angle d theta is the ratio of length of an arc of a circle to the radius of the circle and is measured in radian, denoted by small letters RAD. It is defined as the angle subtended at the center of a circle by an arc of length equal to the radius of the circle. Solid angle is defined as the ratio of the intercepted area dA of the spherical surface, described about the apex O as the center, to the square of its radius r, and is measured in steradian with the symbol SR. If the magnitude of the intercepted area is equal to the square of the radius, then the solid angle is equal to 1 steradian. Accuracy and errors in measurement. In measurements, accuracy and precision are two important terms. For example, if 5 dots are thrown and all hit the bull's eye, each throw is said to be accurate and precise. Accuracy is the degree of closeness of the measured value to the true or actual value. How close the darts land to the center of the bull's eye determines the accuracy of the throw. Precision is the degree of resolution of a measured value when the same quantity is measured with different devices. If all 5 darts land with the same point, then the throws are said to be precise. Take, for example, an object whose absolute length is 32.56 mm is measured using two different instruments. Using the first instrument with resolution of 1 mm, we obtain the measurement as 32 mm. Let us call this measurement M1. Using the second instrument with the resolution of 0.1 mm, we obtain the measured value as 32.5 mm. Let us call this M2. Here, M2 is more accurate as it is closer to the object's true value than M1. Also, M2 is more precise as the resolution of the instrument used is greater than that of the first one. Any quantity that is measured should be accurate and precise, especially in science and technology. In reality, however, measured values carry uncertainty. This uncertainty is called an error. Errors are classified as systematic errors and random errors. A systematic error is a unidirectional error, that is, it is either positive or negative. A systematic error can occur due to an imperfect instrument, a faulty measurement technique, or incorrect process of measurement. Errors may occur due to an imperfect use of instrument for measurement. Such errors are known as instrumental errors. For example, if the needle of a simple balance is skewed or bent, it always shows a weight that is more or less than the actual weight of the object being weighed. Errors may occur due to an imperfection in an experimental technique or procedure adopted while measuring. For example, keeping a thermometer under the armpit will not measure the body's exact temperature as the mercury bulb is exposed to external factors such as air in the room, humidity, etc. Errors may also occur due to incorrect technique or procedure being followed by measuring values. Such errors are called personal errors. Parallax is one such error. While measuring the length of a line using a foot scale, if you tilt your head, the length measured will be shorter or longer by a millimeter or two. Systematic errors can be minimized or eliminated by using a perfect measuring instrument and by improving the technique or procedure of measurement. Random errors are akin to what they are called, random. These errors vary in terms of sign and size, that is, they can be either negative or positive, and the quantum of errors varies in absolute terms. These errors can arise out of unpredictable situations, such as a sudden change in environmental conditions, voltage fluctuations, or mechanical vibrations in the experimental setup, etc. Random errors can be minimized or eliminated by ensuring that the measurements are taken under stable conditions and using properly set up instruments. Another type of error is least count error. This can be associated with both systematic and random errors. Least count is the smallest value of measurement that can be measured using an instrument. All values are considered precise up to the least count of the measuring instrument. For example, if you are using a meter scale, its least count is 1 millimeter. Hence, any measurement error will be in multiples of millimeters, not less. In academic laboratories, the general equipments used to measure length are a vernier caliper and a screw gauge. The least count error in a vernier caliper is 0.01 cm and for a screw gauge is 0.001 cm. Least count error can be minimized or eliminated by using high precision instruments or improving experimental techniques. Another way to reduce such errors is to repeat the measurements and take the arithmetic mean to bring the measured value closer to the actual one. If n measurements are taken, say A1, A2, A3, A4 and so on till An, then the final value will be taken as the arithmetic mean of these n measurements. In the absence of the true value of measurement, this arithmetic mean is treated as the true value. The magnitude of difference between true value and each measured value of a quantity is called the absolute error of that measurement. It is denoted by mod delta A. Since an arithmetic mean is considered the true value, delta A1 is equal to A1 minus A mean. Delta A2 is equal to A2 minus A mean and so on till delta An is equal to An minus A mean. Individual error. Delta A may be positive or negative. However, absolute error mod delta A is always positive. Mean absolute error is the arithmetic mean of absolute errors of all measurements. If we take a single measurement instead of n number of measurements, then the true value of the measurement lies on the range A mean plus or minus delta A mean. This implies that any measurement of a physical quantity A is likely to lie between values A mean minus delta A mean and A mean plus delta A mean. Instead of absolute error, we often use relative error. Relative error is the ratio of mean absolute error to mean value of the measurements. Relative error is denoted by delta A. When relative error is taken in terms of percentage, it is called percentage error. When a quantity is derived from more than one measured value, the error in the derived quantity may be a combination of errors in the value from which it is derived. For example, the volume of a cuboid is the product of its length, breadth and height. If there is an error in the measurement of length, breadth and height, then the error in volume will reflect the combined effect of all three errors due to mathematical operations. Some common combination errors are errors of a sum or a difference, error of a product or a quotient, or error in case of a measured quantity raised to a power. When two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. If the two physical quantities have their measured values A and B, and mod delta A and mod delta B are the absolute errors, find the error delta C in the sum C is equal to A plus B. We have by addition C plus or minus delta C is equal to A plus or minus delta A plus B plus or minus delta B. The maximum possible error is C. Delta C is equal to delta A plus delta B. For the difference C is equal to A minus B, we have C plus or minus delta C is equal to A plus or minus delta A minus B plus or minus delta B, which is equal to A minus B plus or minus delta A plus or minus delta B plus or minus delta A plus or minus delta B, or delta C is equal to plus or minus delta A plus or minus delta B. The maximum value of error delta C is again delta A plus delta B. When two quantities are multiplied or divided, the relative error in the result is the sum of relative errors in the multipliers. Suppose a measurement Z is equal to A into B and the measured values of A and B are A plus or minus delta A and B plus or minus delta B. Then Z plus or minus delta Z is equal to A plus or minus delta A multiplied by B plus or minus delta B, or Z plus or minus delta Z is equal to AB plus or minus B delta A plus or minus A delta B plus or minus delta A delta B. Dividing left hand side by Z and right hand side by AB, we get A plus or minus delta Z by Z is equal to 1 plus or minus delta A by A plus or minus delta B by B plus or minus delta A by A into delta B by B. Since delta A and delta B are small, we shall ignore their product. Hence, the maximum relative error delta Z by Z is equal to delta A by A plus delta B by B. This holds true for division as well. The relative error in a physical quantity raised to the power k is k times the relative error in the individual quantity. If z is equal to a square, then delta z by z is equal to delta a by a plus delta a by a is equal to 2 into delta a by a. Hence the relative error in a square is twice the error in a. In general, if z is equal to a to the power p into b to the power q divided by c to the power r, then delta z by z is equal to b into delta a by a plus q into delta b by b plus r into delta c by c. In this module, we will be learning about significant figures. Whenever we measure the length or weight of an object, we note the measurement in the form of numbers. Here's a brick. Let's measure its length. Observe that the length is between 15.4 centimeters and 15.5 centimeters. Since we are not sure, we can say that the length is approximately 15.45 centimeters. In this measurement, 1 and 5 in the whole part and 4 in the decimal part are certain, while the 5 in the decimal part is uncertain. This 5 is uncertain because this is an approximate value. The values of many measurements in real life are decimal numbers. Digits in decimal numbers can be categorized as certain and uncertain. The number of digits in a measurement which are certain plus one additional digit which is uncertain are together known as significant figures. There are rules to determine the significant figures in a given number. The first rule says that in any measurement, all non-zero digits are significant. For example, we weighed about steel that measures around 62.45 kilograms. Here, all the digits are non-zero numbers. In this case, all the 4 digits are significant figures. The second rule says that in any measurement, all the digits including zeros are significant for a decimal number greater than 1. Here, we have the length of the water hose, which measures 6.407 meters. This number is greater than 1. There are 4 significant figures in this number. The third rule says that in any measurement, if the decimal number lies between 0 and 1, the zeros to the right of the decimal point but left to the first non-zero digit are non-significant figures. Consider any number, say 0.006452. Observe that there are 2 zeros between the decimal points and the first non-zero digit, that is 6. These zeros are non-significant figures. Hence, the significant figures in this number are 6, 4, 5, and 2. Therefore, the number of significant figures is 4. The fourth rule states that if the measurement is a whole number, then the case becomes ambiguous if there are zeros to the left of an understood decimal point, but to the right to the non-zero digit. To remove this ambiguity, the number should be reported in scientific notation, that is, a into 10 raised to the power b. For example, let's take a number 2507000. This is a whole number. According to rule number 1, there are 7 significant digits in this number. However, in this number, there is an understood decimal point which is usually not written. The rightmost non-zero digit in the number is 7. There are 3 zeros between the 7 and the understood decimal point. We can report this in scientific notation as 2.507 into 10 raised to the power 6. Now the number of significant figures in this number is 4, since 2.507 is greater than 1. The fifth rule says that in any measurement, all the final zeros in a decimal number obtained by rounding of a decimal to given number of a decimal places are significant. For example, let's take the number 9.8982. There are 5 significant figures in this number. Let's round off the number to 2 decimal places. The resultant number 9.90 has the digit 0. But this number is greater than 1. Therefore, 0 is also a significant number. The number of significant figures in this number is 3. Using the rules we just studied, decimal numbers can be rounded off to the required significant figures. There are certain rules to round off the uncertain digits in a given number. The rule by convention says that the preceding digit is raised by 1 if the insignificant digit to be dropped is more than 5 and is unchanged if the latter is less than 5. Here is an example. We will round off 8.917 to 3 significant figures. This number has non-zero digits, and there are 4 significant figures. In the decimal place, we will round off 7, resulting in the number 8.92. Here is another example. Round off 7.9342 to 4 significant figures. This number has non-zero digits, and there are 5 significant figures. In the decimal place, we will round off 2, resulting in the number 7.934 as the number to be dropped, which is 2 is less than 5. Now, consider two numbers, 3.945 and 3.975. Let us round them off to 3 significant digits. In this case, the insignificant digit to be dropped is neither greater than nor less than, but is equal to 5 in both the given numbers. To do this, we have another convention which states that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Thus the answers are 3.94 and 3.98 for the rounded off numbers as shown. Here, the length can be written as 8.1 plus or minus 0.1 or 8.1 plus or minus 1.2%, and the breadth can be written as 5.1 plus or minus 0.1 or 5.1 plus or minus 2%. Hence, using the combination of errors rule, the area of the field calculated as the product of these two quantities would be 41.31 plus or minus 3.2% or 41.31 plus or minus 1.3 square meters. We can report this as 41 plus or minus 1 meter square. Here, 1 square meter is the error in the result. Thus, the result has also 2 significant digits, which is the same as the original data. Rule number 2 says that the relative area of a value of a number specified to significant figures depends not only on n but also on the number itself. If there are two quantities, say 10.01 meters and 80.5 meters, both carrying an error of 0.1 meter, then the relative area in 10.01 meters is plus or minus 1%, while the same for 80.5 meters is 0.12%. Another important point to remember with significant figures is that intermediate result in a multi-step calculation should be taken to an additional significant figure in every measurement than the number of digits in the least precise measurements. Consider a number, say 6.55. The reciprocal of 6.55 taken to the same number of significant digits, that is 3, is 0.152. However, the reciprocal of 0.152 is 6.58, which does not match the original data we had. Now, if we consider the reciprocal of 6.55 to 4 significant digits, we get 0.1527. The reciprocal of 0.1527 taken to 3 significant digits is equal to 6.55, which is functions and dimensional equations. We learned earlier about different physical quantities, of which 7 are considered fundamental according to the SI system of measurements, while the others are derived physical quantities. The 7 fundamental quantities are length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. These are also referred to as base quantities. All other physical quantities can be conveniently derived from these base quantities. Thus, we have relationships between fundamental quantities and derived quantities. Therefore, when a derived quantity is expressed in terms of base quantities, the resultant expression is the product of different powers of the base quantities. For example, consider the quantity force. Force is product of mass and acceleration. Mass is a base quantity, and acceleration is a derived quantity, which is the ratio of change in velocity to time. Velocity, which is also a derived quantity, is the ratio of displacement to time. Displacement, in basic terms, is length. Thus, velocity can be expressed as the ratio of length to time. Using the same logic, we can write acceleration as length by time divided by time. Thus, the expression for a quantity force can be simplified as shown. From the expression, it is clear that the exponents of mass, length, and time in the expression for force are 1, 1, and -2 respectively. These exponents of base quantities in the expression of force are called dimensions. Thus, the dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. We say that the dimensions of force are 1 in mass, 1 in length, and -2 in time. For convenience, we use symbols to represent base quantities as follows. For mass, we use m. Length is denoted by L and time by T. The other 4 base quantities are represented by symbols of their SI units, namely electrocurrent by I, thermodynamic temperature by K, amount of substance by mole, and luminous intensity by CD. The physical quantity expressed in terms of its base quantities is enclosed in square brackets to show that it is an equation among the dimensions of the quantity and not among the magnitudes. Thus, we can write the expression for force as force equal to mLT power -2 as shown. Such an expression for physical quantity in terms of its base quantities is called its dimensional formula. An equation which equates the quantity with its dimensional formula is called the dimensional equation. Of the 7 base quantities in the SI system, we see that only 3, namely mass, length, and time, exist in the dimensional formula for force. Thus, we can say that the dimensions of all the other 4 base quantities in the expression for force are equal to 0. In mechanics, most derived quantities are related to only the 3 base quantities of the 7, namely mass, length, and time. Let us look at another example. Let us find the dimensional formula for pressure, which is equal to force per unit area. Area is the product of length and breadth. Length and breadth represent the base quantity, length. Thus, area can be expressed as length square, and hence its dimensional formula is L power 2. We know that the dimensional formula for force is mLT power minus 2. Now, the dimensional formula of pressure is obtained as shown. Following the same methodology, we find the dimensional formula for the volume of a body. Volume is a product of length, breadth and height. Height also represents the base quantity length. Thus, the dimensional formula of volume is L power 3. Similarly, we can find the dimensional formula of mass density, which is the ratio of mass to volume. The dimensional formula for density is ml power minus 3. So far we have discussed derived physical quantities, namely force, pressure, and density. These quantities have units, namely Newton, Pascal, and kilogram per meter cube respectively. But there are certain derived physical quantities that do not have units. For example, relative density is the ratio of the density of a substance to the density of water. As it is the ratio of two identical quantities, it does not have any unit. Therefore, the quantity relative density does not have any dimensional formula. Another example is absolute refractive index, mu, of an optical medium, which is ratio of the speed of light in air or a vacuum to the velocity of light in the given medium. Refractive index is just a number and significant even though it does not have any unit, because the value of mu of a medium indicates the extent to which a ray of light bends on entering medium at a given angle of incidence. Refractive index of a given medium is constant and does not have any dimensional formula. You will learn about refractive index in detail later in the course. We also have certain physical constant, each of which has a unit, as well as dimensional formula. For example, the universal gravitational constant G is a constant whose value is 6.67 into 10 power minus 11 Newton meter square per kg square, and is denoted by the expression G is equal to force F into distance d square by mass m square. Thus, the dimensional formula of G is obtained as shown. We obtained the dimensional formula of G as m power minus 1, L power 3, T power minus 2. You will learn about G in detail in later chapters. So far we have discussed physical quantities, which are expressed as the product of base or other derived quantities. We also learned that the dimensional equation is the equation among the dimensions of the quantity and not among the magnitudes. But we may encounter such situations where we need to add or subtract different terms involving base quantities. It is very important to know that when we write L plus L, as shown, we mean length added to length. So we get length again, which is not 2 times L, as we are not adding the magnitudes of length. Similarly, if velocity is subtracted from velocity, we get velocity. Thus, Lt power minus 1 minus Lt power minus 1 equals Lt power minus 1. The table shows the list of some of the physical quantities and their dimensional formulae. You will learn about the applications of dimensional formula later in the course.